thank you very much for inviting me. It's great to be here. 6 years ago, I lived in Delhi for 4 months and I've come back a few times since. So it's always good to be back. So our approach is to use big data and latest empirical and computational methods to calculate the costs of climate change for the entire global economy. And we're doing this one step at a time. This is not going to be when we finish with this project, it's not going to be the end of this question, but I think we're highlighting a new way to do this, and it will allow us to improve upon this as the years go forward. So as I said, we want to calculate the social cost of carbon. That's the cost associated with emitting a single ton of carbon into the atmosphere. So for example, the increased mortality due to increasing heat waves because of that carbon emission is a component of this cost, as are many other things. So we have a very simplistic kind of description of what happens here. So we have production occurring somewhere which releases CO2, which changes the climate, which impacts human well-being, which again feeds back into production and consumption. The models that try to capture this, that try to calculate this social cost of carbon, they're called integrated assessment models, or IAMs. I might use that phrase again by accident throughout the rest of the talk. When they first came around in the 1990s, they were this very big step forward in how we understand the climate economic problem. But really, they haven't been updated since then. So current policy which tries to set this value, the social cost of carbon, is based on information from 20 years ago. And as I said, there's been a kind of revolution within our understanding of this in the past 5 or 10 years. So the problem that I'm specifically going to focus on is how we do damages. So how we understand those damages on different sectors. So the problem with those models at the moment is that it currently calculates the economic damages as best guesses or estimates something based on very limited information, but hasn't used all the empirical evidence. In those models, we don't really understand adaptation. There's been no serious effort made to try and calculate the costs of adaptation for any of these impacts. And it also, even when it does use evidence, it's very geographically biased. A lot of the research which comes about this, particularly the research which was there 20 years ago, was coming from the United States. There are very few small set of countries, and so it's biased towards impacts in those countries and not in others. So we're trying to fill in these gaps. This is what those damages look like in the old set of models. So each line refers to a different model that is used to calculate climate economic costs, and this is how it calculates its damages. This is temperature increase on the x-axis, and this is the damage to global GDP, or as a proportion of GDP. So if the world heated up to 6 degrees Celsius above the pre-industrial average, there would be anywhere from a 4% to a 10% loss of global GDP. The problem is with all of these is that they're basically made up by someone sitting in an office and not knowing what is going into these. For each of those 3 models, this is just measuring the number of papers, the number of actual estimates, the pieces of evidence that were used to estimate, to calibrate what those damages are. So for these 3 models, you see that they used probably 1 paper from the 90s, a couple from 1998. This one has only used a few from the early 2000s. What we're using in our effort, and the y-axis is the same here, is in total about 400 different estimates from papers which have mostly come out after the last paper in these ones. So this is where the evidence has happened. There's been a real explosion of it, and this is what we're using to inform our damages. Okay, I won't dwell on this for too long. But our advance here on the intellectual side is to make sure that the damages satisfy a certain set of criteria. They need to be really scientifically robust. We need this to be the best scientific evidence possible. So we want them to be causal. We want to know that it's not just that sicker people live in hotter places. We want to know that the heat causes people to be sick. We want to make sure that it reflects adaptation and that we do this based on data, and that it's representative of the areas that it claims to be representative of. So we don't just take what damages look like in the United States and apply them everywhere in the world. This is probably not so interesting, but the history of this, based on my two main criteria, whether it's causal and whether it accounts for adaptation, it's been a slow process which has occurred over the past couple of decades. So these initial things that I showed, basically they weren't either causal or didn't account for adaptation because people made them up. There's experiments where you will, for example, in a greenhouse, you can make a greenhouse hotter and watch as plants grow less and measure that, but it doesn't understand what people do in the real world about adaptation. You can look at how people are different across space and you understand how they adapt, but you don't understand what the causality is. And then my advisor and the head of EPIC, Michael Greenstone, really pushed this literature forward a lot by actually getting at understanding causality in the real world. And now what we're doing is a method which I'm going to explain, which will help us do both of those things at the same time. And this is really only, as I said, 2012 or so was the first time that we started being able to do this. So we go through this whole process. It's not important that you read this. We'll walk through each step of this process, and I'll spend time on each one as we need to. But we're going to study a case study in particular for all of this, which is going to be mortality. So mortality is likely to be one of the largest costs associated with climate change. Increasing heat waves will lead to increasing numbers of deaths. And so we're going to look at that as an example here today. This is what baseline mortality rates look like around the world. Everything I'm going to say to you now is going to be expressed in deaths per 100,000 people. So it's always taking account of population. This is what the present looks like in terms of temperature. This is the number of days on average across the world at different temperatures. So they're on a global average. There are about 120 days around the world that are at 28 degrees Celsius. And that's what that means. This is the present day. And this is what the future looks like. So you can see that the cooler days, there's many fewer of them in the future. And for the warmer days, there's a lot more. So we want to understand what's going to happen to mortality as we go from this world in the blue to this world in the red. So we do our first step, where now I'm going to walk through how we develop that actual estimate of the relationship between temperature and mortality. So first of all, we need data. So what we've done is we've collected mortality data covering these countries in the dark green. And that covers about 47% of the global population. So this is the complete data on deaths in each of these countries. And by including China and India, we managed to get ourselves up to 47% of the population. Without them, we would have a lot less. We've increased our data now, where we're up to about 58% of the global population. One place where we have very little data is sub-Saharan Africa, and that will remain a problem, because data availability there is very low. Okay, if you're an econometrician and you want to pay attention to the equation at the top, please do. If not, keep your eyes down on this part of the slide. So what we want is we want to have data that follows a person or a country through time. In our case, we have data on countries or on districts or sub-districts within those countries that each year tells us what the mortality was in those districts or counties or whatever. It's pretty difficult to find this type of data for a lot of countries. A country needs a pretty sophisticated national registry of births and deaths, which surprisingly few countries actually do have. So now I want to just talk through some of the insights which allowed us to calculate this in a causal way, and what you need to be careful of when we try to do this kind of estimation. So one of the biggest challenges is that every death from a heat wave isn't necessarily a death that wouldn't have happened otherwise. We call this phenomenon displacement. So we can have a situation where we have mortality, and this is the average mortality rate in any day of the week, any year, and this is time on this axis. Suddenly we have a heat wave, or it could be this can be anything. It could be a really bad air pollution event, like here was last week, and you will see a lot of extra death in the data. But if you follow this through time, and then it starts to decrease. If you follow this through time, in almost every single one of these situations, you will see a decrease in the period afterwards. So let's say this was days, and we have 5 or 6 days here, we have a heat wave, and a lot of people die. And then for the 2 weeks afterwards, we see that there's actually fewer deaths than there would be otherwise. So what's happening here is that we have displacement. So it's the case where there's people who, if we're thinking of heat waves, people who might have had weak hearts, might have been very sick in hospital, who probably would have died in the 4 or 5 days afterwards, who died a few days early. And while that's important, if we want to think in terms of the total economic cost of this, we want to make sure that we're counting the deaths that would not have happened otherwise. So in a way, we want to try and sum up this and subtract them. So we know only what the extra effect on people who wouldn't have died otherwise was from this. So that's one of the things we account for in econometrically. We'll account for lots of different lags. And it's surprising how few researchers would have done this with relation to mortality temperature. One of the other things that's important here is that we'll often need some other controls for different characteristics in the country, like population growth rates or income, healthcare access, electricity access, air conditioner usage, something that's changing over time that we can measure, because then we can account for certain things that might be driving these results. And probably the most important insight is this one, which in econ speak would be referred to as fixed effects, but this is the intuition behind it. So let's say we have 2 locations. Let's say we have one district in America, one district in India. So this is temperature, and this is the outcome. Let's say it's mortality here. The district in India has much hotter temperature, and each one of these dots, let's say, represents a year and the mortality rate. So the Indian districts seem to have a hotter temperature than the US districts. If we do what you would naively do in this situation for research and treat all of these points as the same, we're essentially taking an average of all of those points and fitting one line between them. So what we conclude from that is that as temperature gets hotter, mortality decreases. And that's the way a lot of this work was done for years and years. And in fact, a lot of the work on those old models is based on research like this. But there's lots of reasons why there's differences between any 2 places. And they could be the temperature's different, but also the income's different, the education is different, the culture is different, the investments people make to protect themselves are different, history, geography, everything could be very different. So what we want to try and do is account for all of these things we don't observe in order to try and get at the actual causal relationship between these 2. So instead of just connecting these dots and treating them the same, we actually fit a response to each one separately. So then we're able to get what the general relationship is between temperature and mortality that accounts for the fact that these places are very different in many other ways that we don't observe. So that's what these terms account for. It's these fixed effects. And that's probably the real insight here that allows us to get to causality in our estimates. In particular, what we do, so this is a group of US states, all of which voted Republican except for the last one, which has been on my mind in the past week, thinking about doing environmental work. And what we actually do is instead of estimating something for the whole world, we're estimating one of these responses between temperature and mortality for lots of different geographic units. And that allows us to say something about adaptation, and we'll come back to that a little bit later. If we were to run this whole global thing, this is what we get. So this is temperature and the excess deaths per 100,000, and this is the real result from the data that I spoke about before. So we see that for the number of days, if this is the average temperature within our sample, it's 18 degrees or so. As the number of days at hotter temperatures increases, mortality goes up compared to what it would be at this average temperature. And as the number of colder days increases, mortality also goes up. So all this is saying that as it gets colder or as it gets hotter, people start to die more because of temperature. So this is kind of interesting, and you probably you can realize this now already. There's lots of places where there's a lot of cold deaths, because in northern latitudes, and they're going to heat up. So if their temperature on average is down here, there's a lot of extra deaths because of the cold. And as that shifts, as their temperature shifts more towards here, they're actually experiencing fewer deaths. And calculate for the whole world what this actually is. The lives saved by climate change and the lives ended by climate change. And that's the important factor that we're trying to get at here. So that's what we've estimated, and that's the core part of our research here. So now we need to try and do two things. We need to try and understand adaptation. There's a lot of things that are going to change about the world as we go forward into the future. And we also need to try and understand what do we do in all of the countries where we don't have data to estimate this. I showed that map and it had 6 countries on it. We've increased it now to 20-something. But it's still not all of the world. So what do we do about that? To give a sense of to give some intuition for this is the United States. And I'm going to highlight parts of the United States which are different deciles of temperature. So these are the counties or the districts in the United States that are in the 10% of the coldest districts in the United States. Okay? Does that make sense? And if we only look at, let's only look at this part of the effect here. So in what I'm going to plot on the other thing, it's just the effect of really hot days on mortality. So for the cold counties, when you have a really hot day, you have a large mortality effect. But as you get hotter on average, you go more south, this mortality effect starts to decrease. And it gets smaller as you go through down to the warmer countries. So this is this effect here. So you can see that the effect of mortality of a really hot day in these hottest places is much smaller than the effect of the same hot day in colder places. And that's because of adaptation. The colder places didn't need to invest in air conditioners. So when it goes to 35 degrees Celsius in a day, they have no air conditioner to turn on. People down here not only have air conditioners, but they also understand behaviorally what to do. If it's extremely hot out, maybe you don't go outside, you don't go and exercise that day, or you take some different adjustments. So there's a lot of things that can be going in here, both investments in something like air conditioning and different behavioral changes across this sample. So that's the intuition that we're trying to get for adaptation here. We've estimated in each of these places what the relationship between temperature and mortality was, and then across space, because some places are hotter than others, that response is also different. So now we can ask the question, what happens when this part of the country heats up because of climate change and its temperature is more like these places? So it's probably reasonable to assume that this place here will start to see a lower mortality rate because people will make those investments and will start adjusting their behavior. So that's how we're dealing with adaptation here. But we're not only looking at temperature, we're also looking at some other factors. Now, we've chosen 3 for the moment. There's other results we have about how the age of the population affects this, which is a really big effect. Partly this is limited because we have to try and use these data for every country on the planet. And some countries, South Sudan, for example, has very limited data that it can use for this. So it's a much richer thing, but we're trying to explain it with very few factors. And it actually explains a lot of what's going on. So we care about temperature. We care about income. Richer people are more able to adapt, more able to make those investments, buy air conditioning, for example. We care about population density. So the importance of this really came from a paper that Professor Greenstone did about temperature and mortality in India, and found a big difference between rural areas and urban areas. Urban areas had much lower mortality from heat waves than rural areas. So we want to try and include that and those changes through time. This is how these things change. So let me try and explain this. On the x-axis, this was the temperature. This is the temperature of the places around the world where we have collected all of our data. This change on the y-axis is basically the change in mortality in that area based on increasing either temperature, income, or population density. So to give an example of that, here, this means that as the average temperature increases, it's exactly what we saw in the United States. As the average temperature increases, and this is negative, the impact of temperature on mortality decreases. Not very much happens for the middle temperatures, and you see a decrease in temperature as the average number of days in the cold temperature increases. So all this is saying that the more that I experience either a very cold temperature or a very hot temperature, the lower that the mortality will be in that place. We see a similar pattern for income. And this is real data, so it's very noisy and does some things that we don't like, but that's what happens when you use real data for things. Focusing on this one, if you're at a place, if you're experiencing very hot days, so days above 32, 33 degrees Celsius, the richer you are, so as income increases, the lower your mortality is. So this is negative. And the same here, on the lower end, by and large. So income is actually protecting people from hot and cold temperatures, not doing very much in the middle. Population density, similarly, interestingly though, it seems to be that living in a city is better for helping you with cold temperatures rather than helping protect you from hot temperatures. Again, in this global sample. So that's how we characterize adaptation. What that lets us do is, by knowing those three things, income, average temperature, and population density, we're able to take this thing that we estimated for 46% of the population and apply it to all of the population, because we know those factors for it. So I pick somewhere in South Sudan, and I know the temperature, the income, and the population density. I know how our previous results varied with those things, so I can predict what it would be here. And I should say here that if we ever get data on mortality from South Sudan, we would be able to put that into our estimation, and maybe it would be different than this, but this is based on all the information that we have at the moment, which I think is pretty comprehensive so far. This is the best prediction possible. We've tested this by trying to predict these for places that we know the mortality response, and it does very well. But this is what the increase in mortality, so the color here is the increase in mortality, and this is just focusing on that really hot temperature thing, hot temperature bin. So for a day above 33 degrees Celsius, there's a lot of extra mortality, which happens in, let's try and use this instead of pointing the whole time. There's a lot of extra mortality that happens in coastal India, in China, in places in Russia, across the Amazon and sub-Saharan Africa. But some places are quite protected. So you can see Europe and North America, probably because they're richer, have lower impacts because of those. You can see here, where there's very, very few people living, so as we sum this up globally, this won't have a very big impact on our estimates. But here, because the temperatures are so hot, that's why they're adapted. So adaptation here is happening for different reasons. Okay, so now we know what's happening in all of the world based on this data and adaptation response. So now we want to connect that to what's going to happen with the climate into the future. So to go through this adaptation and to try and capture the cost of adaptation. So just to show you how this changes when we start thinking about the future. We have projections, which are this set of projections agreed upon by the UN, the World Bank, EASA, some other agencies, for what's going to happen to population and income into the future. We have a whole community of thousands of climate scientists telling us what's going to happen to temperature into the future and precipitation and other things. And so we have those all at a very fine scale of different district level things across the world. And so thinking into the future, this is what's actually happening. The red line here is that same curve I showed you before. Temperature and change in death rate. And this is estimated for one district in Haryana. So this is real data from India. And it shows the same thing as before. On very hot days, more people die. On very cold days, more people die. And you see that in most of the Indian data, the cold days are much more damaging, but there's also very few of them. And then this is just because there's almost none of those ever observed in this area. But as I said, this district is getting richer and warmer, and the population is growing through time. So this is for the current period, 2001 to 2020. If we look from 2021 to 2040, the increase in death because of temperature is getting smaller. The same is happening for low temperatures. And if we go through the rest of the 20th century, you can see people are getting more adapted here. So in a way, this is kind of, as a economist, data science something, this is, to me, is pretty magical. This is data really revealing some kind of truth about something that very strongly fits a theoretical hypothesis that we had. So again, that's just that district becoming more adapted through time. Full adaptation here would be a flat line. That would imply that it doesn't matter how hot it got, I would never be at risk of losing my life, or no matter how cold it got. But we don't see many places becoming fully adapted. So what that lets us do is, because we have our population projections, our climate projections and other things, we can project this sensitivity out into the future. So again, this is just for these very hot days. This is the picture we saw before, red meaning that a lot of people are dying because of these hot days in these different places. And it's 2010 at the top. And as we go forward into the future, based on those projections of income and population and temperature, you start to see that the high damage areas, the very sensitive areas, are getting less sensitive through time. So this is basically a picture of the world becoming more adapted. And this is all informed by data and the real relationships in those countries where we estimated this. Until we get to the end of the century, and there's a few places where the income growth has been very low in particular, but still have a lot of mortality. But most other places in the world are getting better, just like that example from Haryana that I showed before. Well, but so this is at the heart of what we're trying to do. I think, personally, that we need to worry about climate change for various reasons, and I've done lots of research in this over the past 10 years, and lots of things have informed that. But I've very rarely seen a global, or never seen a global estimate of this, which accounts for the people who are getting better, the places that aren't as cold anymore, and the places that are getting hotter, that actually looks at the net effect of those. And there's very few estimates of that, if there are any of that. So the question is, your question is the exact reason that we're doing this. Do we have to care about climate change? In the end, we want to do this because if we only look at the very bad places, then we overestimate the effect of climate change. If we only look at the very good places, we underestimate the effect of climate change. What we need to do is take this all together and take it for lots of different sectors, not just mortality, but other ones as well. And then try to do the cost-benefit calculation to actually work out if the costs from climate change are bad enough that we should spend money to make policies, to change our energy system, to invest in air conditioning, to invest in infrastructure, that kind of stuff. So My prior is that we should care about climate change, but we want to quantify it first to know how many resources we should invest in caring about it. It turns out the answer is yes, we should. From this, the mortality still increases enough that it's having substantial costs. But your question of should we care about it is exactly why we're doing this. Just so we can put some precision or definiteness on that answer. Because in the end, if you want to make policy about this, you need to be able to quantify the risk from it. And I should also point out, so even though this is getting towards zero, there's very few places that have negative mortality. They're still positive, even though it's smaller. Oh, and one other thing on that while I'm here. When we value this cost of mortality, when we value the cost of anything around the world, it becomes kind of a difficult issue to think through. If I'm in the United States or in Ireland, where I'm from, the population is pretty wealthy. And so if I lose 10% of my income because of climate change, that's in total dollar terms, that could be a lot. If my income, the average income in Ireland is $40,000 GDP per capita. So if I lose 10% of my income, that's $4,000. There's many places in the world, particularly down here, where the income per capita is on the order of $1,000 or even a few $100s. So if they lose 10% of their income on $1,000, it's only going to be $100. That's a very small dollar value, but it might matter a lot more for them. If we just summed up the whole world just on what the dollars were, it looks like the rich countries are the total cost of this, and that's the problem with just valuing this in terms of dollars. We want to value this in terms of welfare. So it's important to know how much is lost based on what the incomes in those places are, rather than just knowing the total number of dollars that are lost there. And this comes back to a valuation thing that we'll discuss a little bit later. Okay. So for this one again, everything that's happening here, this is just a change in the sensitivity. So apart from the valuation issues I mentioned before, we also don't know what it cost a person here to go from really red to orange, or anywhere in the world, to become more adapted. We don't know anything about the costs. We developed a method to try and estimate this cost. I think we're the first people to try and do this. The first people to do this in a convincing way, I think. Rather than go through all the equations, I'm just going to tell you what the intuition is. So, to restate this, what we have so far is these relationships evolving as they become more adapted, but they don't observe the costs. If adaptation were costless, then everyone would get to a flat response straight away. But we don't see everybody getting to a flat response, so we know there's some cost involved. It becomes too expensive to invest in adaptation. So it's possible to bound this adaptation using a thing called a revealed preference approach. So the intuition there is that if I'm at a location with a certain average temperature and a certain temperature sensitivity in the year 2020, and I have that certain sensitivity, the next year that will change, it will decrease because it gets hotter. That means that somewhere in between, I value the cost of the mortality as lower than the... Well, let me try and do this a little bit better. Sorry? Yes, then lower than the cost of adaptation. So that means that the cost of the mortality to me in the year 2020 is some measure or some bound on what it costs to adapt. And if I change, then I put another bound on what it costs to adapt in the next year. So the mortality that you observe is kind of a measure of what people are willing to pay to reduce the mortality. So that's essentially what we're doing with this. And I can explain that more later. It's much easier with equations, but I didn't want to bore you with all of that. So we do our final piece then once we've accounted for these costs, and you'll see the costs laid out in the next few slides. Just to show you what I'm talking about here for climate change, these are the projections that we're using. This is taking in every single climate model. Again, it's this culmination of a work by thousands of people over the past few decades. And this is what the average temperature looks like now in the historical period, 1986 to 2005. These are the number of days above 28 degrees Celsius, so the number of hot days. You can see it's very hot across the Sahara, as you'd expect, not very hot up in Russia or Canada. And this is what it looks like under a business as usual scenario. So a scenario where we don't really invest in reducing carbon dioxide. So you can see these number of very hot days have increased a lot, and you can see India had very few before and now has a lot of them. This is the projections that are going on behind what I'm about to show you. And that's a change by the end of the century. So let's break this down. This is the change in heat-related deaths. This is the baseline. So 0 here doesn't mean no deaths, it means the baseline that we have currently. And so what I'm plotting here is just the change. And this is time. This is going from 2000 up to 2100. This is, if we don't allow people to adapt, if we don't allow them to change because of income, temperature, other things, this is what the change in mortality looks like for India. So we'd see by the end of the century around 200 extra deaths due to temperature change in India. 200 per 100,000, and the current mortality rate is somewhere around 1,000 per 100,000. So that's a really big increase in the number of deaths. But as I said, people aren't just going to not invest to protect themselves. So now if we just adjust for the income and the population density, the urban effects, we get something much lower. So this is capturing that people have gotten richer and have started to invest. They're living more in cities and they're protecting themselves more. And so the mortality it's almost a quarter now, just from those two effects. If we include the mortality response due to those two plus temperature, so the fact that it's getting hotter, I get more experience with hotter days and I'll buy an air conditioner or something, we actually see a decrease in mortality for India. That kind of implies that we gained so much experience, climate change becomes such a problem that if there was no costs associated with this, we would pay to decrease our mortality. But as I said, there's no cost there. So once we do this process I talked about before, where we use this idea that people would only adapt up to the level of the costs they can accept, we get something which falls within these shaded regions. So it's much smaller than no adaptation, much smaller than just adaptation due to the other ones. But it's still positive, but it's, again, about 1/5 of what it was in the case where there was no adaptation. So this is the result that we get from India. Back to the question of does this matter? We see an excess mortality of around 20, 30 people per 100,000, which is nowhere as large as 200, but it's still a substantial effect. This is what this looks like in the US. The y-axis has changed here. The interesting thing about the United States is the difference between no adaptation and the adaptation for income and population density doesn't really exist. So in the data, that's kind of saying that the United States is at a frontier of adaptation. They've fully adopted air conditioning in most places. There's a few places like in California where they don't, but by and large they are pretty well adapted. And then it's just about the behavioral changes they make because of increased temperature. And this is what this looks like for the whole world. So again, this is the no adaptation, income and population density, no costs, and then this is the final estimate. So around the world, this is looking at something roughly 50 extra deaths per 100,000. Yeah, so this is a little bit weird, and I can go in and talk and explain about what's actually going on there a lot afterwards if you want, but it gets a little bit too much into the details. An interesting thing to note here is in the no adaptation case, and in fact in this other case, you see exactly what we were talking about before. Remember the curve which just said cold days kill people and hot days kill people. The fact that this isn't increasing for a lot of the next few decades is showing that fact, that we're moving away from cold deaths and more towards heat deaths, and they cancel each other out for a long time. until suddenly we get to a point in the middle of the century where we're only seeing extra heat deaths. Okay, so what do we do with that? How do we get our social cost of carbon? If we take the data that we had before, all that global stuff that went into those maps, and plot it in a different way, we just take the global slice around here, around the end of the century, and plot the mortality response at different temperatures, we get what we're calling now a damage function. So this is the final output of what we want to get, which then will feed into these models. We've put a value on this, which takes the value of a statistical life, which is calculated at the US, and then uses an income elasticity of 1 to apply that to other countries. So basically, people in different countries value their life in the same way as someone in the US does as a function of their income, linearly. So what this shows is that this is temperature change, temperature change at the end of the century relative to the current average. So as temperature increases, you see that mortality increases. So this has allowed us to get a damage function. This is the likely range of this. So this is 66% of the data, and this is the median here. And we've put a value on this. So this is the proportion of global GDP. And so you see that if we are to get a temperature change by the end of the century, the best guess predicted at the moment is about 4 or 5 degrees. We'll likely see about a 10% cost of that just due to mortality on the global economy. This is a non-market good, so it's a little bit difficult to think about that in terms of changing production. But if we are considering this non-market value as all the costs incurred due to people dying, difficult adjustments for family, hospital costs, everything that's included, we're seeing about a 10% change predicted in a business as usual scenario. So we go way back to the start and compare this to what was in the models currently. So you can see that for about a 4 degree, 5 degree change, they were going for about 5 or 6, from about, I guess, 4 to about 7 or 8%. And we get something which is about 10%. Except these ones were meant to be comprehensive. They are meant to include every single effect on the economy completely. We get from one sector cost which is similar, and mortality is likely to be the most costly impact of climate change. So the other ones might, if we add in labor productivity, it might only add a few extra percent. It won't add another 20 on top of this, most likely. But it's showing that from actually rigorously quantifying these things, it suggests that these values and the assumptions they were based on really aren't capturing what's happening in truth in the world. And what we want to do is calculate this social cost of carbon based on these things and not on these. So to actually have evidence and data and use every bit of data that we can to estimate what the costs of climate change are. We're doing this not just in mortality. We've got these sectors at the moment. This is just a measure of the number of estimates we're using for those from different countries in the world. We've got agriculture, crime, conflict, and social stability, labor productivity, health, where there's been a lot of evidence, migration, coastal property damages, and changes in energy consumption. And we're going to apply this same or similar approach to all of those sectors and add in each of those costs. There's, of course, big things missing. Biodiversity and land use change and some other big items, but it's so difficult to value them or to do this kind of thing. We're taking the approach that we should do what we know best first, and if this is any indication, by the time we've quantified the things that we know, we'll already have corrected this calculation so much that it will really spur on climate action. The damages you get from these things is saying that it's roughly $40 per ton for each ton of carbon that I emit currently. This would kind of imply that it's substantially more than that, but we haven't done that full calculation yet. So in conclusion, what we're trying to do here is that for anyone who's doing this work, we want to give this strong recommendation that we apply the best techniques in data analysis to try and understand what these costs are. And that these damage functions as they go into the models really are, first of all, transparent and represent the best evidence that there is.
So this is just sort of some of the data on what I talked about earlier, negative relationships between GDP and output. This is some data from just the Caribbean and Central American countries, but sort of it shows you how across a range of sectors you kind of see this relationship. So, as I said, there are many different mechanisms through which overall GDP might be affected by temperature. When you start looking at manufacturing, also there are many different mechanisms through which this might act. For example, there's a body of literature that looks at conflict. Conflict is the sort of thing that might influence every single sector of the economy. And so when I talk about labor productivity, even within manufacturing, it's only one mechanism that might be influential. So this is a statement that I put in here, which is less, which they've sort of backed away a little bit in the newer reports from the IPCC. But this statement suggests that the vulnerability of industry is primarily coming from extreme events, right? The vulnerability of agriculture has been well known and agreed upon to come from gradual temperature changes also. But this sort of statement suggests that we think about the literature on industrial output and climate change as coming mostly from extreme events. So you have a hurricane, you have a cyclone, you have more flooding, and that causes sharp drops in industrial output. The mechanism we're talking about here, labor productivity, is something that will occur with gradual temperature changes. So you become less and less productive as temperatures increase, and that's an effect that will occur even over small temperature increases. And what I'm going to show you is that these temperature increases don't need to be very high for you to sort of start seeing these effects. So this is basically what I find. So if you want to leave now, this is the time to leave. So large impacts on worker output. So 4 to 9% degree reductions in worker outputs when the wet bulb glows temperatures cross 27 degrees Celsius. Now this is important because, as Amir mentioned, there's a body of literature from the lab. So it's not what we call ecologically valid evidence, in that it doesn't come from the settings that we're examining this in. But that suggests that 27 degrees is the point at which your body starts dropping productivity quite quickly. So you might imagine that when it's very cold, as temperatures rise, you can work more. Then there's a period where maybe the change is limited. But after 27 degrees in the lab, you sort of see productivity drop significantly. Now this is coming from a lot of data collected on a number of workers in different factories, in different manufacturing sectors, and we sort of see this effect across these settings. The second interesting thing that we find here, which is completely distinct from labor productivity once you're in the factory, is the impact of temperatures on attendance. So if you're not showing up to work, and that might be for a number of reasons. It might be because you fall ill, it might be because you don't want to go out in the heat, it might be because the work environment is hot. So, rather than show up there and be unproductive, you choose not to show up at all. So again, looking at these large numbers of workers on whom I've collected some data, we see that for every additional day of elevated temperatures, you sort of have a 2-degree 2% increase in absenteeism. And I'll show you some graphs that sort of are interesting. So you can have two things going on, right? You can have, for any given day, it gets hotter and hotter. And when that happens, you're more and more likely to skip work. But you can also have a sequence of warm days, right? And so a sequence of warm days might also make you more likely to skip work. So these are two separate ways in which temperature might influence absenteeism. I have suffered from 10 days of 26 degrees, and now I don't feel like going to work. Maybe I've fallen ill. Or I suffered from 1 day of 35 degrees, and now I don't feel like going to work, or now I don't show up to work. So we'll separate out those two, and it's interesting to look at those. The third impact, and this is very suggestive, so I wouldn't say, I'd ask you to take this with a grain of salt, with a bunch of salt, but you sort of don't see these attendance impacts on daily wage workers. Why is this important? Daily wage workers are paid to show up, and they are paid by the amount they produce. So if you don't show up to work, the impact on your income is significant. There's a high price you pay for absenteeism. Now if you're a salaried worker, that's not the case. You're on a contract, you probably have a limit of leaves that you can take, but there's a much weaker relationship between not showing up to work the next day and how much you take home at the end of the month. So this is interesting because this gets at how wages and the nature of contracts that you sign with workers might influence these absenteeism effects. There's some data that we have that climate control, so that's air conditioning in a workplace environment, breaks the impacts on worker productivity. That's as you might expect. The workplace is cooler, and so when workers are in the workplace, they're as productive, or at least slightly more productive than they would be if there was no climate control. But it doesn't change the impacts of attendance. And that's, again, interesting because that's sort of intuitive as well. Climate control does not change the environment outside your workplace. And so if absenteeism is in any way driven by what's happening outside the workplace as well, then climate control is not necessarily going to affect absenteeism. And then I look at, this is all 1 to 4 is data at the individual worker level collected from a bunch of workers, as I said, in different workplace settings. I show that this sort of evidence goes up one level. It replicates when you look at surveys of manufacturing plants. And in some sense, the big picture objective of this paper is to say, okay, we see these declines in manufacturing output with temperature right at the top. How do we trace this all the way down? So we start with workers, we go one level up to manufacturing plants, and then we go one level up to aggregate economic output in the manufacturing sector. And in that process, possibly say something about adaptation as well. That part of the paper is very limited. So I'm going to skip some part of this. This is sort of a summary of the lab literature. A lot of the graphs I'm showing you are actually from one paper, from Solomon, who is also working with EPIC. So this is a graph of like a collective of literature from the lab, and the point I'm basically making is that after 25 degrees, maybe a little more, you sort of start seeing this big decline in productivity, and before that, less so. This is why there is a sharp limit on our ability to work when wet pulp temperatures grow higher. It's because we need to dissipate the amount of heat we generate when we are carrying out any physical activity. And our ability to dissipate that heat is coming through when we sweat, the evaporation of that sweat. And so when you can't evaporate enough moisture, you're not able to dissipate enough heat. And when you can't dissipate enough heat, you can't generate as much heat, so you can't work. So there's some work that's been done on this, largely from the agricultural sector, looking at workers in, say, picking fruits in farms, looking at whether people change their use of time. So with time use studies on high temperature days, do they take part in more leisure activities and so on. So that's suggestive, although not directly measured, of absenteeism. You know, if you have more time to do fun things, then maybe you're taking time off work. And there is evidence, and this is old evidence that goes back, that in very physical activities where you cannot really have climate control, such as mining, you have a big problem with heat stress. And so this evidence, you know, I think the first paper on this was written in 1880 or something like that. At least the first I could find. So in that sense, this is not a new idea. But what's different here is we're talking about work that is not physically strenuous. So you're not lifting heavy weights and moving them from point A to point B. You're doing something that physically is not strenuous. So what you need to carry that out is a mixture of sort of cognitive abilities and the ability to repeat a task over and over again. I'm going to skip this. This is just to say that the output of any manufacturing activity or any economic activity is going to depend on a lot of inputs, and one of those inputs is labor. And if that labor is less productive, then it's effectively like taking away some people, right? If that labor is now half the productivity as it was on another day or on a cool day, then that's like losing half the people you have on that hot day. So now let's go through a bunch of tests, if you like, of this proposed mechanism. So I'm going to start by looking at aggregate manufacturing output in India. There are 2 or 3 models that you can fit to this, including completely nonlinear models where you estimate this for different groups of years. Here I'm doing something very simple. I'm saying assume that the change in temperature sensitivity is linear, right? So it's of the form A plus BT, and what we're interested in measuring is what is A and what is B. In other words, how does it change over time? And one of the interesting things you see, and this is something you see when you look at specifications that are nonlinear as well, this is easier to understand, is that if you look at India in 1970, 75, and the effect of temperature on output in those years, and then you look at the effect of temperature on output much more recently, you see that temperature sensitivity has decreased significantly. And this is sort of in line with what Amir was talking about and some of the other evidence that we are collecting, which is that countries like India can adapt. And they can adapt not just as far as mortality is concerned, but they can adapt, potentially adapt, where you're looking at the manufacturing sector and labor productivity. This is important because an upper bound on costs and an easy upper bound on costs is to say what is the cost of air conditioning across your entire manufacturing plant. Maybe you can do things that are cheaper than that, very likely you can, But that's an easy upper bound, because if you do that, you've basically removed the temperature problem entirely. So now I'm going to look at data and show you some numbers from manufacturing plants. This is a survey that India carries out every year. It's a survey of large plants. So these are not necessarily the plants that are most sensitive to temperature effects. But those are the units on which we have reasonable data. And you have a whole bunch of manufacturing sectors. You know where these plants are. There's some intelligence and sort of sneakiness required in figuring out where all these plants are, but I will not get into that. The point is, you can build a time series of these plants and where they are. Because you know where they are, you can match these plants to temperature and humidity data, and we care about temperature and humidity data because we are interested in these wet bulb globe temperatures. And so the question is, do we see anything in these plants and the output from these plants that would be consistent with what we know about labor productivity? One reason to be interested in this is, although we use, and this is something that I still need to do, although I use the entire panel of manufacturing plants, there's a lot of dispersion in where they are located. And that's not a problem right now. But one form of adaptation is for industrial activity to grow in different parts of the country, right? So rather than investing in, for example, climate change, climate control where you are, you might choose to set up your next plant in a part of the country that is cooler. So we don't see that here because we are tracking plants that have stayed in the same place. So I have nothing to say on whether new plants crop up in different places. I mean, you can eventually start saying something on that because you will see new plants in this data set, but I'm not going to talk about that. I'm going to skip these equations. But suffice to say, those equations are trying to estimate plant output, average plant output across this entire sample as temperatures increase. Now I'm using a slightly different definition of temperatures than what Amir is using. I'm using something called degree days. And that's partly driven by the fact that I have less data here. I don't want to go into too much detail on what a degree day is, but a degree day essentially means adding the number of degrees you have across the number of days you have. So 25 degrees in one day and 27 degrees on another day means the 27 degree day contributes 25 degrees in a bin that's below 25 and 2 degrees in a bin that's above 25. So this is the definition of temperature that is normally used by the air conditioning industry, for example, to estimate how much energy you would need to cool an area. So they don't normally use the definition that the economics literature often uses, which is how many days you have in a particular bin. That's actually exactly the same as the degree day measure, but collapsed down. And as you collapse it further and further down, you basically end up with this. But that's an aside. What I want to bring your attention to is these two numbers. So what we find in the data is for days that are cool, and for years that are cool rather, for years that are cool, output seems relatively insensitive to temperature. For years that are hot, and this is the average temperature in the year, you start seeing output decreasing with temperature. So these are plants that essentially this is a plant that, and the cutoff is important because the cutoff is somewhere near where we've looked at the cutoff in the physiology literature, right? So it's it's a cutoff at about 20 to 25 degrees, and then above 25 degrees it gets more pronounced, depending on what specification you use. So this is sort of consistent with the idea that something is happening to these manufacturing plants at temperatures where you sort of see labor productivity go down, and their manufacturing output also goes down there. So this doesn't tell you for certain that it's labor that is driving this, but it's sort of consistent with that story. You can then ask a few other questions, and I'm going to just show you two. One is that if it's labor that is the problem, then you'd expect plants which have a high value added of labor to be affected more, right? So if workers in plants are adding very little value to your final product, then a decrease in their productivity is likely to change output by a smaller amount. When you're adding a lot of value, then you're likely to change productivity by a larger amount. Now, I'll give you an example that is an example actually from my microdata. It's not from these surveys of large plants. Is diamond units. So what a diamond, small diamond plants do in the city of Surat, where most diamonds actually across the world are cut and then delivered to people who put them into jewelry, is they have different stages. And the first stage of this process of cutting and delivering a diamond is a man whose job is to sort out the high value diamonds from the low value diamonds. Now this is a guy who, if he makes mistakes, is costing the firm a huge amount of money. These low value diamonds go to other people, they are sold to other people. The high value diamonds, or the ones that he flags as high value diamonds, are the ones that go up the chain. So this first guy, or these group of people in this diamond unit, are incredibly important. Higher up the chain, where you're polishing the diamond stone, less important. The value you add there is relatively speaking much smaller than the value the first guy. So one of the a crude way of getting at worker value add is to look at output, and you look at the number of workers the plant is employing. And what you see here is essentially, and I don't want to go into this table, but what you see here is essentially that plants where worker value add, by this definition, output per worker, right? Plants where worker value add is high, they're the ones that are most sensitive to temperature, right? So again, that's suggestive. It may not be the only reason, but that's again consistent with the idea that labor productivity has something to do. There are other tests you can do. You can look at plants that are more likely to have climate control as measured by their electricity in non-production activities. The plants that are more likely to have climate control seem to be less sensitive to temperature. You can look at something like what Amir looked at. You can look at places where temperatures are generally higher and places where temperatures tend to be less high. And you can ask the same adaptation question. Do these plants that are in cooler areas respond worse to increases in temperature than the plants that are in hotter areas? You'd expect plants that are in New Delhi, for example, or around New Delhi, to have invested a great deal more in climate control than someone near Bangalore. So in that case, a hot day in Bangalore is probably likely to have a bigger impact on plants that are there than a hot day in Delhi. The hot day in Delhi doesn't matter. I'm going to go now one step lower. Right? We've talked about aggregate output a little bit. We've talked about plants. Now we have to talk about workers, right? So I'm going to give you evidence from various case studies. The first of these is evidence from the weaving sector. The weaving sector is it's the lowest part of the textile industry. So at the end, you have cloth that is made into clothes and then often exported. And we have some data for that too. But the weaving sector is essentially producing low value cloth that is then dyed, that is then cut, that is then sent to someone who is making garments. So there's a whole chain above them. So these are the beginning of that chain. Now this is an important sector. It accounts for 1/5 of India's employment. It actually accounts for more than that because we have very poor data on the informal sector. So the 1/5 you should take as a lower bound. This is more important than 1/5. Because it's generally an informal sector setting, and the setting I'm studying is certainly an informal sector setting, you don't have contracts that workers are given. They're paid in direct proportion to how much they produce. Right? And so these workers can go in and out. You may come to work for half the year, then you go and do something else. Maybe you go back to your farm, someone else comes in your place. So the worker is just a unit, a person that you pay every day per unit of what he produces. This is indoor work. It's not physically demanding because it is essentially mechanized. What these workers need to do is essentially walk up and down these aisles, and they have to look at the spindles that are weaving the cloth. And every once in a while, they have to reset those, right? As one set of cloth is weaved. And typically, one worker is looking after about 6 of these machines. So you imagine this guy; he's basically going back and forth, and he's keeping a lookout on these machines, and then he's resetting and changing the spindles when necessary. So it's not physically demanding, but it does, and you do get a lot of time in between the small thing that you're doing, but it does require you to be on the ball in the sense that you need to be quickly noticing and then quickly acting on any pauses in these machines. So what we did is we collected data for 151 weaving workers over 365 days. So every single day for all of these workers. And this is data on how much each worker produced. And we get that data because we know how much each worker was paid. And they're paid per unit production. That's just a distribution of worker output. Now, why is there that spike at 0? There's that spike at 0 because sometimes people don't show up. That's the absenteeism effect that I spoke about. But the rest of it is sort of normally distributed. Some of these workers are very, very good at their job. But mostly they're sort of tightly distributed around 100 meters of cloth. So this is just to say that this is how workers are paid. So this is a very This simple, is actually also how bottom of the pyramid firm. You weave cloth, then you sell that cloth in the wholesale market. How much the revenue you earn is the wholesale market price multiplied by whatever you weaved. To a crude approximation, most of your costs are how much you pay workers. There are other costs, there is maintenance and so on. But the day-to-day cost is mostly this, the day-to-day revenue is mostly this. And we happen to have good weather data from a climate station sitting right next door to these things. So I'll show you some data from that. The second case site is coming from garment firms that are right at the top of this food chain in the textile sector. So what are these guys doing? They're taking dyed, woven, dyed, quality controlled cloth, and they're cutting and stitching this into garments, and then they're exporting those garments. Again, this is indoor work, but these workers have full-time contracts. They are paid monthly. They're not paid per unit of output. And there is an efficiency measure that the firm measures for every production line. in this firm. So what they do here is, instead of workers carrying out tasks independently, there'll be a group of workers who are carrying out a single task, right? So they go from worker A at the back to worker to the worker at the front, and they all do the same thing. Each worker does the same thing, but what you get out of that line is the combination of the things that the worker does. Right? So unlike weaving workers, these are not independent entities. So we collected daily data again for 194 of these lines, doing the same thing over 2 years this time. And we measured two things. We measured the efficiency, which is the output per hour, and we measured what is called the budgeted efficiency. The budgeted efficiency is a measure the firm calculates, which is basically produced the following way. They get what they call master craftsmen, right? The best performing workers that they have. They make a line with those best performing workers, and then they have them carry out the activities that they want the rest of them to do. So that's sort of like your target. That's your limit. If you hit that, great. Most people don't hit that. If you exceed that, you're probably into the master craftsman thing the next time. But the output of interest is mostly efficiency. The third case study that I'm using is, and the objective of using these different case studies is, you want to see labor productivity not just in one setting, you want to see it in different settings where you would expect different outcomes. So this is data from a steel plant in Bhilai. And so what happens here? This is a plant that employs a significant number of workers, 300 or so workers. However, all these workers are essentially sitting in air-conditioned cabins. That's because the entire process is mechanized. You're not on the shop floor next to the furnace. So you have, in these cases, a mechanized plant with a lot of workers in climate-controlled environments. They're still doing things. This plant wouldn't run without them, but they're not doing things on the shop floor. We have outputs of the output here is something called a bloom, which is part of a railway line output. So we measure the number of blooms that are produced by this plant, and the number of cobbled blooms produced by this plant. The cobbled blooms are failures. So those are blooms that can't be used. So that's where you would see errors coming in if these workers were being affected by temperatures outside. So this is just to say that our data is across different parts of the country. I spoke about the case study sites in terms of what they are, but where they are varies, so it's not just in the same place. So I'm going to skip some of that and sort of come right to the end of this very quickly. So what do we see from our data? Let's look at the first panel. The first panel is from our garment manufacturing plants. And our garment manufacturing plants are of two types. And this is a simple first cut measure. You know, the economists like to sort of do difference in differences. But these plants are of two different types sitting next to each other. And one plant had recently installed air washers, which are a cooling system for the shop floor. The other did not. And so what do we see here? We see that when you install air washers, if anything, production rises as ambient temperature rises. This is partly because these systems start getting switched on. More and more of these start getting switched on as it gets hotter and hotter. But where they aren't, you see this decrease in output. And you see this decrease in output, you sort of see a little bit of, it's a little more flat until around 20 degrees when it starts dropping. Let's look at panel B. Panel B are these same garment plants in a different part of the country. These are all now without climate control. Same thing, you see these workers start becoming less productive at around 25 degrees. Panel C are those weaving workers that I spoke about. Now this is slightly ordered. You do see a clear decrease in output as it gets hot above 25 degrees. You see an increase in output below 25 degrees. That's surprising. If it was very cold, it would have been easily explained, but 20 to 25 degrees is not super cold. But we do find that increase. Now we come to the Bhilai, the steel mill. There's really no temperature effect here. If anything, after 25 degrees, it starts going up. This is the plant which employs a lot of workers. They are all sitting in climate controlled cabins, and it's a mechanized process. So the point being that if you look at these different plants, you see different pictures, and you see different pictures that are again consistent with the idea that in these real world settings, temperature matters for output. So it's not completely perfect and cut and dried, but these decreases after around 20 or 25 degrees for all the places where there isn't climate control, those seem fairly consistent. This is the data on absenteeism. So remember I said that there are those two mechanisms. Now we have data on absenteeism because for all these workers, we know when they showed up. So for a weaving worker, when that worker doesn't show up, it's in our data. For the garment workers, same thing. For the Bhilai steel workers, same thing. So we know when they showed up and we know when they didn't. So what's panel A? Panel A is if you set a temperature of 26 degrees Celsius. So this is slightly above 25, let's say warm. Average temperatures, that means the maximum temperature is likely to be about 30, 32, something like that. So if you set that temperature at 26 degrees Celsius and you start estimating absenteeism as a function of the number of days you are exposed to that temperature. So what this means is I've had 10 days of 26 degrees in the past. What is the effect on my absenteeism today? And so what you see is that in at least the Bhilai steel workers and the garment workers who have monthly contracts, you see that as an increase, as the number of days of exposure increases, the probability of absenteeism increases. You don't see this with the Surat weaving workers. Now there are lots of reasons why you might not see this. One possible reason is that they are on wage contracts, so the cost of not showing up to work is quite high. But again, I don't want to these are not the same places, so I don't want to draw comparisons between them. There are 3 different settings, look at them independently, we see these absenteeism effects in 2. The second set of graphs, which is on the right hand column, that is saying, okay, one for a duration of 10 days in the past, right? So I've had 10 days before me. Temperatures, let me increase the temperature. So 10 days of 26 degrees, 10 days of 27 degrees, 10 days of 28 degrees, and what happens to my absenteeism today?